Could you please give an enormous ISS Tuesday afternoon welcome to Professor Stephen Cowley.
Well, thank you very much. It's good to be here. I'm not sure where I am, but somewhere. Are you having a good time? Yes. Good, good. I'm going to talk about fusion, and there is a joke about fusion that it's 30 years away and always will be. Because we've been trying to do fusion for at least 60 years, and actually, in a sense, really longer than that. It took us about 2,000 years of trying to actually learn to fly. So one day, I really actually think we will do fusion, and we will do fusion to produce energy. I'm not sure we have all the right ideas yet. And one of the reasons I like talking to young people is we need bright people to think about this problem. Because fusion, in some sense, is the perfect way to make energy. It just has one fatal flaw at the moment, is that we don't know how to do it. I mean, we know how to do it a bit, but we don't know how to do it efficiently enough that we can now power light bulbs from it. And surely, right, if it's the perfect way to make energy, it's worth spending your life on. And I've pretty much spent my life on it, so there you go. The story, actually, oh, there's the best fusion reactor you've ever seen. What's that? Yeah, isn't it marvelous? You look at the magnetic field poking out of the edge of the sun. Look at the sunspots on it. It's a plasma at about, well, what you're looking at is at about 10,000 degrees. The center of the sun is at about 15 million degrees. Experiments in my laboratory, although actually I just stepped down from being head of it after 9 years of running the laboratory. Those experiments take the plasma, which we'll talk about in a moment, up to 200 million degrees. So more than 10 times hotter than the center of the sun. And that's the kind of conditions that we'll have to achieve in a very efficient way in order to make fusion energy work. But if you can do that, then you can power the world pretty much for the rest of its lifetime. The world is going to last another 5 billion years. What's going to happen then? Yeah, the sun swells up, becomes a red giant, and we are burnt to a crisp. On the other hand, you'll have lived 5 billion years, so by then you probably will be bored with living. So, you know, it's fine, isn't it? Yeah. The story actually begins with this fellow. In 1920, Sir Arthur Stanley Eddington, who was probably the greatest theoretical astronomer of the early part of the 20th century, he was the guy who took the expedition to South America to measure the bending of starlight around the sun due to relativity in 1917. In 1920, he was president of the British Association for the Advancement of Science. And he had to give the presidential address. And he gave one of the most incredible talks ever in the history of science. Because he took as his topic, what's the sun made of? What's the sun doing? Now, up to this time, there was a theory as to why the sun was hot. And that theory goes back to about 1860, 1870, and around about that time, Lord Kelvin, up in Glasgow in Scotland, it's a long way up from here, not so far up from Oxford, had postulated that what actually the sun was doing, and what stars were doing, was that they were great big balls of gas, and the gravity of that ball of gas was pulling it inwards. And as it pulled it inwards, it made it hotter, because that gravitational potential energy, as it fell towards the center, was being converted into heat. So as it pulls in, it gets hotter. As it gets hotter, it gets pressure, which pushes out. And it then gets to what we call an equilibrium, where the pressure pushing out is balancing the gravity pulling in. But it radiates the heat away as sunlight. And as it radiates the heat away, the pressure decreases and it shrinks a little bit further. Then it radiates a bit more away and it shrinks a little bit further. And it radiates a bit more away and shrinks a little bit further. And Kelvin, who was a very devout Christian, said, okay, we can then figure out how old the sun is, because we can work out how this process works, and we know how much energy is being radiated by the sun, right? We can measure it, and he had measured it. And from that, you could calculate the rate at which it was shrinking. And you could tell, if it started essentially from infinity and fell all the way in, how old it would have been. And he said 20 million years old. Well, 20 million years old was the wrong answer. It was really upsetting to Charles Darwin, because 20 million years old wouldn't be long enough for what he was seeing in the fossil record to have been the origin of life on Earth. It didn't make sense. It made sense to Kelvin because he believed in Genesis, but it didn't make sense to Charles Darwin. Wind the clock forward to 1920, and Eddington says, no, Darwin's right. It doesn't make sense at all. There are stars out there we know are so far away they must have sent their light from more than 20 million years ago. And they look just like our star. And there are geological processes that must have taken longer than 20 million years. The sun must be a lot older than that. So how can it be older than 20 million years and still be radiating energy? So where did the energy come from? Now, in science, it's good to be lucky. It's good to be smart too, but it's good to be lucky. And just around about the time that Eddington was doing this, just before, Francis Aston in Cambridge had a very precise mass spectrometer. What does a mass spectrometer do? It measures the masses of atoms. And he had measured very precisely the mass of hydrogen and very precisely the mass of helium. Aston didn't comment on this, but Eddington looked at this, and he looked at the spectrum of light coming from the sun, and he said, aha, the sun has mostly hydrogen and a little bit of helium in it. Maybe what the sun is doing is converting hydrogen into helium and getting the energy that it's radiating away that way. So he's very lucky, because Aston had just done these measurements. So up to that time, you couldn't tell. There wasn't enough precision to tell that, in fact, helium is a little less than 4 times the mass of hydrogen. So Eddington postulated, and this is pretty remarkable, because at this time we understood that atoms have a nucleus and the electrons go around the nucleus. We understood that from Rutherford in 1909. But we didn't really know what was in the nucleus up to this point. But Eddington said, imagine that what the sun is doing is somehow taking 4 hydrogens and converting it into helium. If it did, there's some missing mass. And Eddington was a specialist on relativity at that time, and of course he knew the most famous equation in physics, E equals mc squared. And he said, if there's missing mass, maybe that mass is being converted into energy, and maybe that energy is the energy that keeps the sun hot, and the sun is then radiating away that energy. So you can, the clever thing about this is you don't actually have to know much nuclear physics, because all you have to know is the mass that you started with and the mass that you ended up with, right? And the difference in the mass times c squared is the amount of energy that you would get out. So if you took 1.008 kilograms of hydrogen and by this mysterious process converted it to 1 kilogram of helium, those 8 grams that you have used, right, would give you 7.5 times 10 to the 14 joules of energy, which would roughly power an individual's life for 10,000 years. Not 5 billion, but 10,000 is pretty good. So just 1.008 kilograms of hydrogen would do that. It's a remarkably large amount of energy. And really, the question is, where does that come from? How does that actually work? See, the clever thing for Eddington is he didn't have to know that. All he had to do was say that we start with 4 hydrogens and we end up with 1 helium. He knows how much energy will come out. He doesn't have to understand the process. For instance, watch the charge on the left-hand side of the nuclei. 4 positives, right? On the right-hand side, helium has 2 positives. So actually, Eddington realized this, and he realized that somehow those 2 of the hydrogens, the 2 of the protons in those hydrogens must be neutralized. And he imagined that actually they captured 2 electrons somehow and became neutralized. But he didn't know how, but it didn't matter because it didn't change his calculation. He then went on and estimated the age of the sun if, he said, the sun has burnt 1/3 of its mass into helium. And he got 10 billion years. That's actually remarkably close to what we now understand. What's actually interesting about this, and it's a big lesson for anybody in science, is he didn't do anything very complicated. He didn't cover the blackboard in Messel functions or, great big calculations or anything. He just thought, and he made a little calculation, he put it together and said it's very plausible that what the sun is doing is turning hydrogen into helium. Indeed, that's exactly what the sun is doing, but it took another 20 or so years before we understood the mechanisms by which you can take 4 hydrogen and convert them into helium. It goes by pairs at a time, and it's called nucleosynthesis, and it's the basic process which all stars start with when they start with hydrogen and build up helium. Now, some stars go on from there. They take helium and they make carbon. And then some stars go on from there and they take carbon and they start to build up all the building blocks of life. It's a rather nice thought that we're all made from stardust. Binding energy. Well, where does that energy really come from? We've said it's somehow converting mass into energy. But this really actually stretches your mind a little bit because actually you haven't changed the number of particles in there. You've changed the character of 2 of the particles in there. So to understand what's happening inside the nucleus of an atom, you have to understand that there are 2 forces that really dominate nuclear physics. There's a 3rd force called the weak force, which plays a role in radioactivity, but dominates the structure of the nucleus. Now, what a nucleus is made of? Protons and neutrons. Yes, very good. You're all incredibly smart, so I'll keep asking you questions. It just makes me feel good. So there's a ball of protons and neutrons there looking like a nucleus. Right? Now, the thing is that neutrons and protons, because of something called the Cowley principle, cannot occupy the same state. And so you can't just pile up a ball of neutrons because that's not energetically favorable. You have to mix in some protons. These 2 forces act in different ways. So if you take 2 protons and they're a long distance apart, they have a positive charge and a positive charge. And due to electricity, what happens between 2 positive charges? Repulsion. Right? But if you bring them very close together, there's another force that acts, and it's called the strong force in the nucleus. And it's very strong, but only at a short distance. And if you can see in the yellow, I've shown a picture of the potential energy of bringing 2 together. Right? At far distance, the potential energy is up and it wants to roll away from each other. So if that's, do I have a pointer here? One of these?
Yeah.
You'll have to look at the middle one because I'm not going to point at all of them. So from this radius on outwards, this radius on outwards here, it repels. But if you bring them closer to that, it attracts. And that's what sticks. The strong force is what sticks the nucleus together. So imagine bringing up protons, protons, protons. You get very, very close, and there's an attraction felt by the strong force. Now, of course, the neutron is neutral, so it doesn't have that repulsion. But you can't make a nucleus without protons and neutrons. Right? Now, inside this nucleus, when they attract, it changes the energy. And energy is mass. So we can work out what the binding energy of a nucleus is by taking the mass, let's do it in the middle here. The mass of the nucleus times c squared, well, that's the total energy of the nucleus itself. This is the mass of the proton times c squared. That's the energy contained in the mass of a proton. This is the mass of the neutron times c squared. This is the number of protons inside the nucleus. This is the number of neutrons inside the nucleus. So if all those neutrons and all those protons were just scattered around and they weren't in that nucleus, their total energy would be the number of protons times the energy in a proton, the number of neutrons times the energy in a neutron. But when they come together, they attract each other, and that attraction is energy, and that energy is reflected in the mass, and so this is always bigger, the bare masses of all the separated neutrons and protons is always bigger than the mass of the thing when it's glued together. So if I subtract those, and then I divide by the number of protons and neutrons, I define a thing called the binding energy per nucleon. And that tells you roughly about a nucleus, right, how well bound it is per particle in the nucleus. And a very stable nucleus would be a one that's stuck together extremely well and has a lot of binding per particle in the nucleus. Imagine bringing up another particle and sticking it on the outside of that nucleus, right? You'd ask the question, would the energy go up or down, the binding energy per nucleon? So, one of the first things people measured about nuclei is this property. How well stuck together is it? Well, obviously, the proton is not stuck to anything. So hydrogen, as a nucleus, has no binding energy at all. But actually, hydrogen comes in 3 isotopes. Anybody know the names of the 3 isotopes of hydrogen? Protium, deuterium, and tritium. I guess there's 3. I forgot protium. Normally just call that hydrogen. It's actually quite kind of a remarkable, because they're very, very different isotopes. This is the binding energy of deuterium per nucleon. Just that formula applied to deuterium. This is the binding energy of tritium, right? This is hydrogen. That 1 means the number of protons. That 3 means the number of protons plus the number of neutrons. Right? That's the tritium. Up here is helium. 2 protons and 4 nucleons. You can see it's extremely well bound because it has a high binding energy per nucleon. Right? Something happens here. So you start with small ones, And they want to stick together because they've got this strong force hanging out the outside of the nucleus, and other particles want to stick onto that nucleus. And so if you take hydrogen and stick it together and somehow make helium, right, you'll have more binding energy. And that's indeed what Eddington was calculating. Right? There's little anomalies here due to the nuclear structure, but the best, as it were, the most stable nucleus is basically this one up here. It's iron 56. It's not quite, but we always say iron is the most stable, but it's not quite, but it's the most abundant stable nucleus, iron right up here. So that's right in the middle of the periodic table. Now, as we go out to heavier and heavier and heavier elements, we get out here to bismuth, and this is uranium, pretty much the heaviest naturally occurring element there is. We can make heavier ones, but this is what we see as the heaviest in nature. Uranium-238 right out here. And what you'll notice is this is not, once you go past iron, adding more doesn't help you. What happens to uranium? It can split in half. It can fission, right? And that's because actually half of a uranium, the two halves, have less energy than the uranium itself. So it's energetically favorable to split into two halves and have those two. Why is uranium less stable? Why don't you want to stick more onto the edge of uranium? Right.
So since the nucleus is so large, it does not attract this at the edge.
But there's also another force, right? What's that doing? Absolutely, absolutely. The combination of those two answers is brilliant, right? The edges of the nucleus are being repelled to the other side of the edges of the nucleus when you get to a large nucleus. The strong force only acts over a short distance. So, but the electromagnetic force, which acts over a longer distance, so what's happening, basically, is my nucleus is getting a lot larger than this radius here. So the edges of the nucleus are feeling the repulsion due to the protons inside the nucleus, which have charge, and it wants to get smaller. So basically, most of nuclear energy can be understood entirely in terms of this diagram. What stars do is they start with hydrogen, and they start building up all these elements up to iron. And then some of them collapse and explode and overshoot in supernova explosions and make all these elements up here. But actually, most of what we see are the elements down here up to the stable point. There's a little bit of overshoot due to various out of equilibrium effects, but that's mostly what we see in nature. Eddington himself pointed out, though, that right down here, we can get energy by sticking the small nuclei together. That process is nuclear fusion. And it's a remarkably steep curve right here as we build it up. So it's a very efficient way of extracting energy from the nuclear processes. However, the sun is rather a pathetic fusion reactor. Even in the middle of the sun, it's doing about 200 milliwatts per cc, per centimeter cubed, of fusion. Now, if you wanted to make a power station that's producing a gigawatt, right, it would be ginormous at that low power density. And this is because putting 4 hydrogens together to make helium is a very difficult fusion reaction to do. The sun can do it because it's very, very big, and even though it's very low power density in the middle, it's so big but that by the time you've added all the power from all of that volume, you get a heck of a lot of radiation. We couldn't be doing that reaction as a way to make power. But this is where something very nice happens. Of those reactions, now, if you want to make a fusion reaction happen, you've got to get one nucleus and another nucleus, and you've got to push them together. And you've got to push them together because at distance they will still repel. It's only when you get them within about 10 to the minus 14 meters that they actually stick to each other. So if you want to make fusion work, you have to get your fusion constituents together. Now, the easiest fusion reaction to do is between tritium and deuterium, the two isotopes of hydrogen, the two more exotic isotopes of hydrogen. In my picture, protons are green and neutrons are blue. I don't know what color they are. Of course, they're not a color. So that if you need to get deuterium and tritium together, you have to bring them in against their repulsion, ram them together until they get within about 10 to the minus 14 meters. And then the strong force will take over. Now, this reaction has a probability of happening, what we call a cross-section, which is 100 times more than the next easiest fusion reaction to do. And one of the reasons is because it's got the least charge, and the other reason is because it forms an almost stable nucleus when it comes together. Now, you bring these two together. What substance have you got when you bring tritium and deuterium together? What nucleus? Helium-5. But helium-5 isn't stable. But it's almost stable. And when it forms, for people who really hot shots, it forms in the J3 hard state of helium-5. So if you spin polarize deuterium and tritium, you get a bigger fusion reactivity. It was my first paper. Anyway, deuterium and tritium come together. It makes helium-5 for about 10 to the minus 20 seconds, and then spits out helium, normal helium, that's 2 neutrons and 2 protons, with an energy of 3.5 megavolts of energy. Right? That's just the way we measure energy, and I'll give you the conversion in a moment. And a neutron. This is one of the fastest neutrons any nuclear reaction ever produces. Typical neutron that you get out of fission is about 1 MeV, mega electron volts. This neutron is 40 MeV, so it's more than 10 times larger. So this reaction here, easiest fusion reaction to do. But really, it doesn't take off till you get to about 100 million degrees. And its peak reactivity happens at about 300, 400 million degrees. We don't usually take things up quite to that temperature, but that's where its peak reactivity. So what do I mean, temperature there? Temperature means basically the energy of the particles that are running around. And we can't fire deuterium and tritium just by aiming, right? That's impossible, right? Your eyesight isn't good enough. What you've got to do is you have your deuterium and tritium running around, and it bumps into it every time. Most of the time when it bumps in, it glances off. And it glances off, and it keeps going. But it's running around, bumping in, and every now and again it hits smack on, and when it does, it fuses. And when it does fuse, it releases the helium and the neutron. Now, in order to get enough energy that when it's randomly moving around and it hits smack on, it gets close enough, you've got to have enough energy to go up that hill of the potential energy to get to the top and fall in, right? And the energy you need is equivalent to a temperature of about 300, 400 million degrees. I'll show you some graphs of that in a moment. Now this we typically need a plasma. We actually work below the optimum temperature, and the reason is if we work at the optimum temperature, the plasma gives off too much light, and it cools itself. So we'll get to that in a moment. We usually work at about 200 million degrees. That's typical. Now, the problem with this, and this would be a beautiful reaction to do except for one thing. Tritium does not exist in nature. Does anybody know why? Yep. Anybody know its half-life? Wow. 12.4, actually. Yes, so no point in, I mean, we can't have a tritium mine. We can't go out there and dig up tritium. So in order to get tritium to power this reaction, there are many ways to make tritium, but the easiest by far is to bombard an isotope of lithium called lithium-6. It's 7% of naturally occurring lithium, and you can find lithium, at the moment, we get lithium from what are called salty brines in the high Andean deserts in Chile. That's where the lithium in your laptop comes from, and in laptop batteries. Now, fusion could use all kinds of lithium because it's so energy dense, the cost of the lithium is going to be negligible to us. So we can use lithium from seawater, and the amounts of seawater, lithium in seawater, it's about 0.2 grams per liter of seawater. And that gives us enough to supply about 30 million years worth of powering the Earth. Now, that won't take us all the way until the Earth has become a crisp due to the red giant, but it takes us a lot further than any other fuels. And presumably, by the time we've had 30 million years of deuterium-tritium fusion, we'll have figured out to do the harder fusion reactions like deuterium-deuterium fusion. Now, when the neutron comes in and bombards lithium-6, it makes another helium and a tritium. And what you do is you take that tritium, you put it back in your reactor, you react with some more deuterium, and you make some more helium and a neutron. Where does the deuterium come from? Seawater. 1 part in 6,000 of the hydrogens in seawater is deuterium. It's quite easy to separate because it's an isotope separation process, but it's twice the weight of the protons, and so much easier to separate than, say, uranium-235 from uranium-238. Right? So actually, your fusion reactor that works off this reaction has to have something that's at 200 million degrees, and anything at 200 million degrees is a plasma. We'll come to that. And it has to have somewhere where you take the neutrons that are produced from that, and you bombard lithium, and you make tritium. And you have to make more tritium than you consume, because otherwise you can't start another plant. So there's various processes where we multiply this, and I'm not going to go into the nuclear physics of that. This is an amazingly energetic process. It's a gift, this fusion reaction. It's by far the easiest fusion reaction, and it's just a little joke that happens to involve one of the most difficult substances to get, tritium. I'm going to emphasize something. Now, if somebody says to you, okay, we've got the perfect energy source, but you just have to heat up your fuel to 200 million degrees, you're going to say, you must be kidding. Right? And I think for 20 years after Eddington proposed that we might think about using this process in order to make energy, I think everybody thought, yeah, you must be kidding. But during the atom bomb project in the Second World War, people actually started to think about how you might do this. And it was Enrico Fermi, the famous Italian physicist, just at the end of the Second World War, proposed that maybe we could hold something at 200 million degrees in a magnetic field. And if we could hold it in a magnetic field, then we could keep it from touching the walls, and therefore it wouldn't be it wouldn't immediately get cold because it touched the walls, and it wouldn't melt the walls because it wouldn't be touching it. And so make kind of a cage out of magnetic field and do this. And ever since then, which was 1945, people have been trying to make a magnetic cage to contain deuterium and tritium and make this reaction happen. One of the things I will do in the next lecture is go through exactly what we're doing, how well we're doing with that, and why we need your help. It's actually interesting just to do a simple calculation. You can do these calculations. They're not hard. They're just the kind of calculation that Eddington did, and he became famous from. So don't poo-poo doing a little arithmetic. If you have a smart idea and you show that the numbers work, sometimes that's all it's needed to do some great science. If you took all the hydrogen in the world's oceans and turned it into helium, it would power the world for 10 to the 13 years. Completely unneeded, of course, to do that much. But it just gives you the order of magnitude of how much energy is contained in that. It dwarfs all other forms of fuel, etc. But imagine we say, okay, but turning 4 hydrogens into helium turns out to be a very difficult nuclear physics problem. Why don't we take 2 deuteriums and turn them into helium? Well, that would power the world for basically 50 billion years. Again, a bit of overkill. The lithium in seawater, about, I've done 3 times 10 to the 6, I meant 3 times 10 to the 7, about 30 million years worth of lithium in seawater. And you can extract the lithium in seawater via the salt in seawater. People suggested that sea salt contains a little lithium. If you actually put sea salt on your food, you're getting a little lithium. And it's a slightly psychoactive salt, so you may be feeling better because of it. Some people have suggested that too. I doubt it. It's so small composition. What are the waste products? Well, if you go back through that, let's look at what we put in and what we take out, right? We're putting in deuterium, and actually we're putting in lithium, because tritium is the intermediary in this process. And we're getting out helium and helium. The amount of helium you will produce for 30 million years worth of fusion is less than the total amount of helium that we had anyway. If that helium was released into the atmosphere, we wouldn't all speak with squeaky voices. It'd be kind of fun if we would, really, but we wouldn't. I suppose we would probably want to collect that helium from our fusion reactors and use it to put in things like superconducting magnets, because it's a great coolant when you want to cool things to very low temperatures, etc. And actually, we are running out of helium, so it would be another source. But we produce so little of it in fusion, it's not really very important. There is some radioactivity produced in this. Because if you remember, we have deuterium, tritium, they come together, they make helium and a neutron. And that neutron coming out, if it smashes into a nucleus in the wall of your fusion reactor, maybe iron, or maybe carbon, chromium, nickel, those are all in steel, it will chip something off the nucleus. It's a tank shell of a neutron, and it smashes into the nucleus and it peels off something there. Sometimes it makes a radioactive nucleus, so it can activate the walls of your device. But we did a calculation, and this is a calculation that says basically how much radioactivity do you have for time after shutdown for one of our fusion reactor designs. And this is what happens in a normal nuclear power station. This is the amount of radioactivity you have, this red line at the top. This is a fusion reactor, and what you will see is it starts already 1,000 times less, and it decays extremely quickly, and in about 200 years, it reaches this black line. That black line is the radioactivity of a lump of coal. So presumably, you wouldn't mind burying your finished reactor in a coal mine because it's going to be no more radioactivity than the coal that's around. So while we do produce a little bit of radioactivity, it's negligible and it decays very quickly. So in that sense, we have essentially a zero polluting form of energy. We don't produce any CO2. We don't produce any of the long-lived radioisotopes that come out of a fission power station. For this reason, and the reason that we've got abundant fuels, that we can, that the waste products are essentially benign, and because you'd be able to produce lots of power in a very small volume, you wouldn't have to cover fields with, with your installation. You wouldn't have to put up great big pylons or whatever to do this. Fusion has been described as the perfect energy source, at least by me. Yeah. So you can do a calculation, and this was done. Actually, it was done in that paper by Fermi in 1945. You do a calculation, and you can say, what is the fusion rate in a box of plasma at a temperature of 200 million degrees? I think actually I should go onto the plasma slide and come back to this. Hold on. I've done this the wrong way around. Now, at about 10, supposing you take a gas of deuterium and tritium, it's just floating around, your deuterium and tritium, as a gas, and you start to heat it up. When you get to about 10,000 degrees, it starts to ionize. But we're going to have to heat it up much more than 10,000 degrees, about 200 million degrees. So it starts to ionize at that point, and what happens is what used to be, the nucleus plus an electron going around it, is a nucleus floating around and an electron floating around. And that's the so-called fourth state of matter called a plasma. Now, the plasma is somewhat distinct from a gas. It can conduct electricity because it's got charged particles. The negative charges can go that way, and the positive charges can go that way. It can carry a current. It can get charged up. It can be affected by a magnetic field. And so a plasma is a distinct state. And actually, most of my career has been working with the physics of plasmas. I've worked on fusion. I've worked on where do magnetic fields come from in the early universe, all kinds of problems that are to do with what is the behavior of a plasma. This is a picture of a plasma in our innovative fusion device at my old lab. This is a device in which we're trying to push down the cost and the scale of fusion and make much better magnetic cages. What you're seeing at that point is an eruption from the edge of the plasma, which is not well contained, not a good bottle at that point, but you can see it glowing. Actually, what you're seeing glowing is the cold bit of the plasma. The really hot bit of the plasma doesn't actually give out any light, it only gives out X-rays. So what you're seeing is the plasma right at the edge where it touches a bit of gas, and then it lights up. This plasma here is at about 30 million degrees, not quite 200 million degrees. So this, imagine you have that plasma, and it's heated up, and don't for the moment worry about how we're going to hold it or whatever. We just heat it up inside a box. And what we have is a distribution of velocities of these deuterium and tritium running around, and every now and again they bump into each other. You can do a not terribly difficult calculation that will calculate the rate at which they will fuse as a function of the temperature that we hold it at. And the temperature on the bottom is given in physicist units, which is in kilovolts here. But basically this, which is 10 kilovolts, is about 100 million degrees. 20 kilovolts. This is a logarithmic scale, which is there. I haven't got my glasses on, so I think it's there. That's 200 million degrees. That's 300 million degrees. And here is the reaction rate of the deuterium-tritium reaction. You can see it peaks around here, 300 or 400 million degrees. So we've got to at least heat it up to 100, 200 million degrees to get right up to these rates. This is a logarithmic scale here, so this is a factor of 10 faster here than it is there. In order to get it to really produce lots of energy, we've got to get it to those kind of temperatures. Those are the conditions for fusion. Down here, negligible amounts of fusion. This here, obviously, is 10 million degrees. You don't really see any fusion happen in any of our devices until you get up into that 100, 200 million degree kind of temperatures. We actually watch this on the jet experiment. When we put tritium inside it, you'll watch as the temperature goes up. There's a very, very steep rise of the neutrons coming out of the plasma as you're getting up to those temperatures. The fusion power is proportional to the density squared, because it matters how many deuterium you have and how many tritium you have, and the chances that they will bump into each other. And you can write down a good approximation to the fusion power in this region is that the power density of fusion is basically this factor times the pressure in the plasma squared in atmospheres, and that's in funny units of megawatts per meter cubed. Now, I put it in these funny units, and we do this in physics a lot, because these are kind of human units. Typical vessel can't hold more. Well, what kind of pressures might we be able to hold? Let's start with the bottom of the Pacific Ocean. How many atmospheres pressure at the bottom of the Pacific Ocean? Basically 1,000, yes, well done, yes. Yes, but we don't want a nuclear device or a fusion reactor, right, that's at the kind of pressures at the bottom of the Pacific Ocean, because you'd have to have walls that were about this thick, right, and this would make it impossible to get inside, etc. A typical fission reactor goes up to about 150 atmospheres of pressure. We typically will take our plasmas up to 7 to 10 atmospheres of pressure in this. Now, megawatts per meter cubed, if you want to make a power station, typical power station, at least on the British grid, is a gigawatt. So, and you don't want your plasma to be more than about 10 meters by 10 meters by 10 meters. So 1,000 meters cubed. So to make a gigawatt, which is 1 billion watts, you want roughly 1 million watts per meter cubed. So in this formula here, or more if you can, right, you're going to need a plasma pressure of at least several atmospheres to make a reasonable sized power station. Anything in which your plasma pressures get up to very large pressures will explode. And we don't want that. It's hard to make a power station out of exploding things. But there is a way, if we can make it almost like an internal combustion engine out of lots of little explosions. I mean, after all, inside the cylinder of your car, every time it fires, there's a little explosion. If the explosion is small enough, it's not a bad way to make power, and that's what we call inertial fusion, and I'll talk about that a little bit. But let's actually look at the scale of the pressure that you might expect in that plasma that you're going to heat up to 200 million degrees. Now, the ideal gas law roughly holds for plasmas of this kind. And the ideal gas law, you might remember, is that the pressure times the volume is equal to the number of moles times the gas constant times the temperature, right? Which you could also write as the number of particles times Boltzmann's constant times the temperature. Or you could write it as the pressure is equal to the density of particles times Boltzmann's constant times temperature. Right? This roughly holds for the plasmas that we're talking about. Right? Because they're actually very, very tenuous, and they behave a bit like a gas at that time. So what is the pressure of a plasma at 200 million degrees centigrade? Well, let's compare the pressure of the plasma to the pressure of air. Pressure of air is at 1 atmosphere, right? So this ratio here is the pressure of the plasma in atmospheres, right? It's dividing that by itself, but at different density and temperature, right? So this is the density of the plasma, particles per meter cubed, and this is the temperature of the plasma. This is the density of air, and this is the temperature of air. Now, temperature of air, let's just take it to be 200 degrees, right? It's near enough because we're not doing precise right now. That's easy because I can cancel the 200 on there, and this makes a factor of 10 to the 6. So imagine I had a plasma with the same density as air at this temperature. It would have a pressure of 1 million atmospheres. Can't be done. Well, it can be done in an explosion, because it would just blow itself up. Right? But it can't be done if I'm going to hold it steady. Right? So what I've got to do is I've got to have a plasma that's really, really tenuous. I've got to have a plasma that's much less dense than air in order to get a few atmospheres of pressure. In fact, it's got to be about 1 million times less dense than air. This is a point I've already made. If we want to make our fusion reactor out for this reaction, I've already spoken for an hour, haven't I? Yes.
Let's take a little bit longer. How much?
No, I guess we didn't start till 10 past. Yeah. But vessels can only hold a few tens or hundreds of atmosphere. And we would have to hold both the plasma and we would have to hold the magnetic field, which we'd make with coils to hold this plasma, if we were going to hold it in a magnetic field. Or I could think about making very, very tiny little fusion explosions. So small that each one released may be, well, typically in inertial fusion we talk about a few hand grenades worth of energy each time. And that turns out to be a fusion explosion of a lump of deuterium and tritium that you can barely see with your eyes. So those two ways in which we might actually make a fusion reactor happen. Here's a picture of the concept that's actually got us to fusion. Now, we'll talk about this next time because tomorrow I'm going to talk about the actual physics of the devices that we're using and why, we think that the next stage, which is the big experiment, ITER in southern France, will actually get to a fusion burn, which will be a world first, probably around about 2030. So not 30 years away from now, about, 13 years away from now. We make a magnetic bottle because particles tend to follow the magnetic field lines. We have to make the magnetic field wrap around on itself. Because what happens to charged particles inside a magnetic field is they make a little spiral around the magnetic field line. And if the magnetic field line leads out of the device, the particles will go out of the device and then they will touch the wall. So if you want to make a cage out of magnetic field, the first thing you want to do is to make sure that your magnetic field goes round in a circle. So you take your solenoid, you've probably all seen a solenoid in school, and you bend it around and you turn it into a donut-shaped solenoid. That's called a toroidal solenoid. So these are the coils round here that make a magnetic field going round in the big circle. Like that. What you also do in this magnetic bottle is you pass a current around this loop. Now the magnetic field in jet is about 3 Tesla. And that has a magnetic pressure, which we'll get to next time. It has a magnetic pressure of about 45 atmospheres. It has a current going round the loop of about 5 million amps of current. So that current that goes around the loop is electrons going in one direction and the deuterium and tritium, the positive charges, going in the other direction with a drift. because actually they're moving around in all kinds of random ways, but on the whole, the positive charges are going that way, and on the whole, the negative charges are going that way. And that produces a current inside there. That current takes the magnetic field that goes around the loop and twists it around. So it wraps around the plasma. And then because light currents attract, the current on one side of the plasma attracts the current on the other side of the plasma, and it squeezes itself towards the center. And when it squeezes itself towards the center, it pulls itself off the wall and isolates itself from the wall. And nothing now touches the wall. The plasma is confined in a magnetic bottle. Well, it isn't actually. It leaks out of that magnetic bottle, and that's our problem. But in principle, it should be confined to that plasma and go round that loop. That device, this device is called a tokamak, and it was invented by a famous Russian dissident scientist called Andrei Sakharov in the 1950s. And the Russians built a few, and around about 1967, they announced that they'd reached 10 million degrees in this device. And we in the UK and the US said, no, the Russians can't have got to 10 million degrees. They can't be doing better than us. And there was a lot of skepticism, etc. And the Russians were measuring the temperature of their plasma in a very shaky kind of way. Actually, they were right, but it wasn't very clear that they were right. And so in the winter of 1967, 3 scientists went from my laboratory near Oxford and took one of their first Q-switched lasers over in crates to Moscow. This is the height of the Cold War. They set up the lasers, and they shined their laser into this, and it bounced off the moving electrons inside there. And the light came back from bouncing off the electrons, and they measured the frequency of the light. How did that tell them what the velocities of electrons were? The Doppler effect, exactly. If a photon from a laser bounces off a moving electron, if the electron is moving away, the light that comes back is redshifted. If it bounces off an electron moving towards you, it's blue shifted. And now all the electrons are moving around at random speeds. If you shine the laser light in there and it's intense enough, the scattered light you will see will be blue shifted and red shifted. But what will happen is you will see it as a spreading of the frequency of the light that's scattered. And from that spreading, you can measure the temperature of the plasma. And so in the winter of 1967, wintering over to 1968, they measured the temperature of the Russian plasma, and sure enough, it was 1 kilovolt, 10 million degrees. And at that point, people realized that this was the best magnetic cage we had at that time. But in 1968, nobody was worried about energy. There's oil coming out of the ground in Texas. There was oil coming out of the ground in Saudi Arabia. Nobody was worried. We hadn't really started to worry about global warming. Nothing was. So people were saying, oh, that's interesting. Yep, we'll build one of those and we'll just move on. And so the experiments in my laboratory and in Princeton in the United States converted to being tokamaks like this, and they built one of these devices. And people started to see temperatures of not just 1 kilovolt, maybe up to 2 kilovolts, etc. But then, early to mid-70s, the oil shock came. This is way before you were born. And at that point, there was oil supplies were cut, and everybody in the West started to worry about energy, and they said, maybe we should accelerate fusion research. And so they put in some money, and they built a big, actually, before we do that, this is a picture on a simulation of what the deuterium ions would be doing in JET, which was the device built with that oil shock money. This is going to play. Yep, there it goes. These are the orbits inside the magnetic field of JET of a deuterium ion. This is a simulation, not actually a measurement, but you can see it going around the field line and moving backwards and forwards here. These are what's called banana particles because they make these banana-shaped orbits. Well, I guess it's not really all that much like a banana, but anyway, that's what we call them. And this is the inside of JET. JET was built as a collaboration between Europe and the United Kingdom. It was started before the United Kingdom joined Europe, and it's going to continue after the United Kingdom leaves Europe. This is the inside. Now, JET has the only machine in the world to produce any significant amount of fusion. This is the inside of JET. I took over running this lab at the beginning of 2008. And in 2010, we replaced all of the inside wall using these robotic arms. These are robot arms. They come on great big cantilevered structures inside the machine. You can't see the back of it. They come in, and they can do all the engineering work inside the machine. We realized that there was a problem of using carbon tiles, like the space shuttle, on the walls. It was absorbing tritium, which is used up some of our tritium, which it's very expensive. It's 30,000 a gram tritium, so we didn't want it soaking up into the walls, and also would produce a danger. And we replaced all of that with, this is beryllium. Anybody know the atomic number of beryllium? 4, very good. This is tungsten down there. Anybody know the atomic number of tungsten? You're counting up. I'll leave you to it. So we replaced the inside of that, and we're about ready to break our own world record, and we're hoping to do that in 2018. The reason I'm stepped down from being chief executive is actually I want to work on the physics and not on the politics. So I'm happy not to be the person who has to go and sell the program at that point. This was the results of the last time we ran any serious amount of tritium in it. This was in 1997, before you were all born, right? In that time, in this device, in a very different configuration of the device, we've improved it since then, we turned on the plasma, we heated it up, in this case, to 230 million degrees, and the fusion power coming out of it shot up to 16 million watts of fusion power coming out of it. The deuterium and tritium, this steep rise is due to the rise in the temperature and pouring out neutrons at this point, and we're measuring the neutrons as they come out to detect how much fusion power is coming out of it. And at that point, 16 megawatts, something nasty happened to the plasma and it went right back down again. But it did demonstrate that we could get 16 million watts. The little kicker is that we were putting 24 million watts of heating power in to keep it warm at that time. So this wasn't even break even for the energy, right? The fusion energy coming out was 16 million watts. We were putting in 24 million watts. So the total energy coming out was 40 million watts, right? But that's not the way to make a power station, as is pretty clear, right? But it did demonstrate that we got the conditions for fusion and that we can make fusion happen. Nobody liked this particular shot. There were many like it, but this was the best of them. I think most of the other ones were just under 15. But actually, what we needed to do was to make a shot in which we raised the temperature, held it steady, and then shut it down. Now, the problem with JET is that the coils that make the magnetic field are made of copper, and they've got millions of amps going through them, so they get really hot when we run the machine. So we can only run the machine for about 6 seconds. So 6 seconds is the longest we can run it at full power. At low power, we can run it for 30 seconds a minute. And future machines will have superconducting coils, so that will be easy to run it for longer. So what the actual discharge, the actual plasma that made people say we could go to the next stage were ones like this, where we brought it up to about 3 to 4 million watts, held it, and then took it gently back down again. That showed that we can control it, we could hold it. etc. But it wasn't as impressive as the 16 million watts, so I always quote the 16 million watts at that time. What that did, and the computer simulations suggest that what we'll be able to do in 2018 is take it up to 16 million watts, hold it, and then bring it back down again. So watch this space next year, probably October, November of next year. Although things always get pushed and pushed. So what people said at that point, see, what was happening in jet is that fusion produces a neutron and the helium. The helium is charged, so it's captured by the magnetic field inside jet. And the helium is got an energy of 3.5 mega electron volts, which is much hotter than the plasma. So the helium charges through the plasma, knocking into deuterium and tritium, giving them more energy and giving up its energy to the plasma. But at 16 million watts, the energy coming out in the helium was only 1/5 of that energy. 4/5 goes to the neutron from momentum conservation. And so only 1/5 of that, so we're only talking about 3 megawatts of heating due to the fusion itself. So we had 24 megawatts coming into the plasma, plus 3 from the self-heating due to the fusion, heating this plasma. But what we want to get to is a burning plasma. And a burning plasma is where the fusion makes enough heat to sustain the plasma so that we can turn off the external heating. This is like lighting your fire. When you light a fire, when you first do it, you put the match to it, and you take the match away, it goes out. But if you get it hot enough and the fire gets going well enough, you can take the match away and it will self-sustain. And you can even put another log on the fire and it will keep burning because the heat produced by the fire sustains the fire. What we want from fusion is the helium that's produces enough heating that it keeps the plasma at 200 million degrees, that allows us to do more fusion, which keeps the plasma at 200 million degrees, so it's self-sustaining and it's burning. And after the results from jet, it was agreed that the way to do this was to make jet ×2. Here is the building, the assembly building for it. This is called ITER. This is the most expensive experiment ever to be constructed. It's going to cost about 15 billion euro. It's being constructed, really nice place, southern France, right, near Aix-en-Provence. In Provence, beautiful place to have an experiment. The wine is good, the weather's good, it's not like being in England. And this experiment is basically jet on steroids. It's twice the size, it's got more power, it's got more heating, and the coils are superconducting coils so that we can switch them on and make discharges, the plasmas, for thousands and thousands of seconds. This is being built by a consortium of Japan, China, South Korea, Russia, the European Union, the United States, and India. We're pulling our resources because to make something where you ignite a fusion burn and it just sits there and burn will be one of the most historic experiments ever, and I'm hoping I'm going to be there. It's getting touch and go now. I have to keep running in order to make sure my heart holds up long enough to be there. But the day we actually are in the control room of ITER and it begins to burn and we stop the external heating and the plasma just keeps going, that's like making a little star. It's just sustaining itself by its fusion burn. And the computer simulations suggest that ITER will get to that. It's an experiment. So there is some uncertainty whether it will happen. But if it does happen, I sure want to be there because it's a historic moment in science. It isn't the demonstration that we can make commercial electricity. It's a demonstration we can make electricity, but it's not a demonstration that we can make commercial electricity. Commercial electricity would mean it would have to cost a certain amount in order to make a gigawatt power station. And at the moment, 15 billion for this one experiment suggests we haven't got all the ideas straight yet in order to make it commercial. But before before we decided to build 747s and fly the Atlantic, we had to have the Wright brothers actually get off the ground and fly. And this is getting off the ground and flying. This is the, it's rather beautiful actually, this polished stainless steel on the outside. This is actually not the building in which the experiment will be. This is the assembly building. This is the building building the superconducting coils over here. This is where you can see it's the toroidal donut shaped. That's where the machine is going to sit, right there. There's a crane right in the middle of that. And to give you scale, here are the people. Right? It is a phenomenal experiment. It has huge amounts of electricity. It has huge cooling because all those superconducting coils have to go down to 4 degrees above absolute zero. It's the most incredible piece of kit you've ever seen. Let's hope it works. It's not the only attempt to get to a fusion burn. And a few years ago, around about 2010, they started, and I'm less of an expert in this kind of fusion, at Lawrence Livermore Lab in California in the States, they started the National Ignition Facility, which is an enormous laser, the world's biggest laser. And the idea of this laser is you have a little pellet of deuterium and tritium inside a plastic shell. It's less than 1 millimeter across. And you fire the lasers onto this pellet. The edge of the pellet ablates, and the rocket effect drives the pellet towards the center, heating it up as it goes. And the deuterium and tritium gets to ignition temperature. And then you're supposed to get a little fusion burn happen inside this. And the thing explodes with about the force of a couple of, or maybe 3 hand grenades. Just that tiny little pellet, like that. This experiment started in 2010. Last week, they doubled their fusion output, but they're nowhere close to a burn at the moment. Almost 2 megajoules of energy comes out of the laser, 2 million joules of energy, and they've made about 30 kilojoules of fusion. So we're sort of, well, factor of 100 off at that time. Tomorrow morning, I'll start to tell you about the problems and why we aren't quite there yet. It turns out that neither of these schemes are working perfectly. And they're really plagued by the instabilities and the turbulence that goes on inside them. In this experiment, you're trying to squeeze this tiny little capsule down to 1/10 or 20th of its size. And it's a bit like trying to, you take a balloon and you wrap your fingers around it and try and squash the balloon down with your fingers. And what happens, of course, is it's never perfect, and it pops out the side, and the little thing pops out the side. And those instabilities, which are called the Rayleigh-Taylor instability, mean that you're trying to squash it, and it just pops out. And it doesn't get up to the temperatures or the densities that you want to make these little explosions. And so that it makes a little bit of fusion power, but it doesn't make anything close to the power that you need to replace the energy that you put in to squeeze it down to those levels. And in the magnetic fusion case, what we find is that though we've suppressed most of the instability, if we look inside the plasma, it's bubbling away. The middle is at 230 million degrees, and the edge is at 10,000 degrees of the plasma. And that temperature difference between the middle and the outside is causing bubbling, very much like the bubbling you have in a saucepan where you heat the bottom, and the top is cold, and therefore the hot water rises to the top and the cold water goes down. The same thing is happening in our plasma, which means that the hot stuff is going outwards and cold stuff is coming inwards, and that is cooling our plasma faster than we can heat it. And if we could reduce that turbulence, we could make jet ignite. And the thing I would like to do with the last years of my research life is to have the ideas that will bring down the cost and scale from the ITER-sized machines to something smaller than jet. If we could do that, then we could get commercial fusion, and then we'd have the perfect energy source. See you tomorrow morning. Oh, questions?